Sanmesh, Sanmesh, am I audible?
Yes, sir.
Okay. Just confirm me whether the screen is visible or not. The screen
Yes, sir. It is visible.
visible. Okay. So I think we'll start the class now. Like we can share this recorded video. Recording is on that side.
Yes, sir.
Okay. Thank you. So coming to the next part. So last class we discussed about some theory part and uh, equations, writing the equations for the solar air heater. Now today we'll discuss as like in flat plate collector. Any disturbance in the audio and video?
No, sir. It's fine, sir.
Yeah. So coming to the again efficiency factors or heat removal factor and finding the performance parameters of solar air heater or any other devices. So today we'll discuss like collector efficiency factor, that is collector efficiency. See here, what I have shown in the collector efficiency factor is, so here FR is the heat removal factor, collector heat removal factor. So this we have seen in the flat plate collector also while discussing about the performance. But here also we'll discuss these useful heat gain, heat removal factor and efficiency factors. So efficiency is nothing but the useful heat gain or the ratio of useful heat gain to the heat supplied by the collector to the fluid. So fluid may be different, maybe a liquid or air or different type of chemicals can be heated in these collectors. So similarly here today if I take the definitions, because without definition one cannot understand what is the importance of these factors. So coming to the collector efficiency factor, so that also represents the ratio of actual useful heat gain rate to the gain which would occur if the collector absorber plate were at the local fluid temperature or the ambient fluid temperature. So if the absorber plate is maintained at the local fluid temperature, which is flowing at a given temperature of the fluid, if the absorber plate is maintained, and once we start with the heating of that air after some time, so that type of ratio of actual heat gain by the solar radiation, where the absorber plate is earlier maintained at local fluid temperature. So that is called as collector efficiency factor, that is F dash. So that F dash on the left side you can see here in the air heater after simplification we can write it as 1 plus overall heat loss coefficient UL divided by heat transfer coefficient, that is HE, whole bracket raised to minus 1. So using this equation one can find out the collector efficiency factor, that is F dash, for the solar air heater. Now coming to the other parameters. So other parameters like collector efficiency factor is over. Now we'll discuss the useful heat gain. So useful heat gain is, as I told, this is also can be written in terms of ratio of actual useful heat gain to the useful heat gain. So that can be a efficiency. In that useful heat gain we have discussed many times. Say for example, whatever the useful heat gain is there, that is obtained from the collector for a given area on which the solar radiations are falling, and using this collector efficiency factor F dash and overall loss coefficient UL, also the fluid outlet temperature to the ambient temperature or the average temperature to the ambient temperature. If you know all these parameters, one can find out the useful heat gain. So useful heat gain, you can see the equation here, FR into AC in bracket solar insolation or the solar radiation S minus overall loss coefficient into inlet temperature of the fluid minus T ambient. So using this equation one can find out useful heat gain, or else we can also go by this equation if we know the FR value. One more equation. Okay, I think in the liquid flat plate collector we were using this useful heat gain MCP delta T. You can see here on the bottom side left side, MCP delta T is nothing but the useful heat gain by the fluid. For that, using F dash also you can find out this values, or else if you know this FR value also, one can find out with using inlet temperature of the fluid, one can find out using the FR value also. So either by collector heat removal efficiency or the heat absorbed by the fluid and the collector efficiency factor. So either by collector efficiency factor or heat removal factor, one can find out the useful heat gain by the fluid like air. So I hope this point is clear to everyone. Any one of the equation you can use to find the useful heat gain parameter. The next parameter is the heat removal factor, which is very important. How much heat? So by and large, you can just understand that F dash or the FR, the heat removal factor, if I tell, that is nothing but how much heat is removed from the absorber. Like this, you can remember. Or by definition, if you see, the heat removal factor is the ratio of actual useful energy, okay, actual useful energy gain to the useful energy gain if the entire collector were at the fluid inlet temperature. This is very important. Earlier definition we have seen when the absorber plate has the same fluid temperature. At that point, once heating starts, what is the collector efficiency factor we have found out by taking the ratio. Now taking the ratio of actual useful heat gain, that is QU, divided by the useful heat gain if the entire collector plate or the absorber plate, if it is maintained initially at the fluid inlet temperature. If the inlet temperature comes, that is the heat removal factor. So in the air heaters, the equation can be written as FR equal to mCp, okay, m dot Cp divided by overall loss coefficient UL into plate area, that is AP. So plate area will be less than collector area. And some cases, if the dimensions are similar, because in the air heater you can see there will be no tubes or no surface changes. It will be complete flat surface, which is almost equal to the collector area or the open area. So that area can be taken here as a plate area or the collector area into bracket 1 minus e raised to minus of f dash ul ap divided by mc. So using this entire equation, one can find out the heat removal factor. Similarly, here also it is written mCp divided by overall heat loss coefficient, area of the collector or area of the plate, 1 minus e raised to minus of f dash. F dash is the collector efficiency factor into overall loss coefficient into area of the collector by mCp. So mCp is nothing but mass of the air and Cp is the heat capacity of the air at constant pressure. Now next part is, so one more part was there in the flat plate collector. If you remember, we were discussing in the liquid flat plate collector, that is a flow factor. In some of the examples, if they ask the flow factor, that is nothing but the ratio of heat removal factor Fr to the collector efficiency factor F dash. So if I take the ratio of Fr to F dash, that is Fr divided by F dash, that becomes the flow factor F double dash. So that parameter is not taken here, but that will be taken for the liquid flat plate collectors. That is the flow factor. Okay. Next, coming to the other side. So as in the liquid flat plate collector, we have seen example like water will flow either in the laminar or the turbulent flows. So whenever this turbulent flow comes into picture or a fully developed and turbulent flow, in such cases we are going to discuss about the Nusselt number. So depending upon the roughness of the inside surfaces and the type of heat transfer, like convection if it is there, then we need to find out this dimensionless number, Nusselt number, using the Reynolds numbers. All of you know why Reynolds number is very important, because we will decide whether the flow is turbulent or laminar depending upon this Reynolds numbers. So if the Reynolds number is more than 2300 or 2500, we judge that the flow is turbulent. If it is less than that 2500 or 2300, we take the Reynolds number or the flow is laminar. So in that cases, if the flow is completely turbulent, okay, we have two equations here, especially for the solar air heaters. So Kayes and Malik, they have given the two equations. So both equations will give you within 10% error. The results will be within 10% difference. So any problem if you solve, if it is given within 10% differences, we can accept that results. So similarly, one Nusselt number is given by case, that is 0.0158 into RE raised to 0.8. This you can use, or else directly if you know the characteristic length L0 of D0. So here D0 is taken because it is a duct. We talk about the duct of air, the passage of the air. So length of that passage of the air is denoted by D0 here, or some cases DE here. So this duct characteristic length D0, H is the heat transfer coefficient by convection between air and plate or air and glass, that H value divided by K. So I think many of you know that in Nusselt number is given by HL by K as a general equation. Here same thing, L is replaced with D0. And also Reynolds number, how to find out, all of you know. So in many anything is related with flow, we always talk about the Reynolds number to decide the turbulency or the laminar type of flow. That is given by rho Vd by mu. So this diameter D0 is nothing but the characteristic length or the section in which the air is flowing. So coming to the another equation for the turbulency, that is given by Malik, that is 0.0344 RE raised to 0.75 divided by 1 minus 1.586 RE raised to minus 0.125. So many cases what will happen is, as the given equations will be found in the data handbooks, or else in the complete given question, the different parameters as well as the correlations can be given in the problem itself. So using those correlations, you can solve the problems. Or else, based on the conditions in the problem, you can go through the data handbook, either heat transfer data handbook or the solar data handbook, you can find out. There, one can use those correlations for a given result, Reynolds number and different characteristics. That Nusselt number can be used, and you can find out the later part. So why we are using Nusselt number? Because either we can find out without knowing this H value, without knowing D value or K value, one can find out Nusselt number directly by Reynolds number. That's one advantage. Once you find out this Nusselt number, later anything if it is unknown here in these equations, so any one unknown value can be found by HL by K equation or HD0 by K here. And generally for the air ducts, the D0 value can be found out if the characteristic length is not given or flow length is not given. In such case, we can find out by using this 4 into cross-sectional area of duct divided by wetted perimeter. So it is a wetted perimeter means inside perimeter of the duct which is in contact with the fluid, means 2 times width plus 2 times height. If you take, that will give us the total perimeter of the rectangular or the square type of duct. So I'll repeat, to find the characteristic length D0 for the solar air heaters or any heaters which is having a duct of a square or rectangular type, one can take 4 into cross-sectional area of the duct. The cross-sectional area is rectangular or square type, then divided by inside perimeter or the wetted perimeter. Now next part is in the testing of the air heaters or the finding the efficiency parameters of the air heaters, one should also find out the pressure drop. So this pressure drop can be found out by instruments like manometers. We'll see in the later class where we are discussing the testing of the solar air heater. In that case, we are going to find this pressure drop. By that instruments you can find out, or else the Blasius equation, he has given one equation to find the pressure drop, which is a dimensionless number here. Okay, so how that to be found out? So he has given some factors here. So using this 4FL rho V square by 2 dE, which relates like Darcy-Weisbach equation, what you have studied in the fluid mechanics, if you remember. So that Darcy-Weisbach equation was friction losses, for finding the friction losses in the pipe. Similarly here for pressure drop, he suggested this equation 4FL rho V square by 2 dE. So dE is nothing but D0 only, how we have found out earlier. L is the length of the passage, rho is the density of fluid like air, V is the velocity. Now coming to this F is Either it is a friction factor or also it is called as a roughness factor of the given surfaces. So for a smooth surface, if it is a smooth surface or little bit very less roughness is there, in such cases we can go by this factor. That is, F can be given by 0.079 Re raised to minus 0.25 if the surface is smooth. If surface is rough, then we have to mention this F factor, or from the data handbooks if available, you can select that F factor. So by this one can find out from the inlet to outlet or from given point to other point, how much is the pressure drop by a number. Okay. Any doubts here up to this discussion? So here we have discussed only the simple definitions and some equations which will be relating the heat transfer phenomena in the solar air collectors. Okay. Anything to be discussed here?
No, sir.
Okay. Yes, I think before going to this problem on solar aerator, a simple type of problems, because here, see, why I'm telling you these type of problems also simple, because the data will be completely given in the problem. Okay, once we know the phenomena or the procedure, at least what is the procedure to be followed, so that we can answer these questions. So one should focus on the questions, what is asked in the problem. To answer that, what will be the procedure by using these given details. Okay, so you need not to worry about how to remember the procedure or how to remember the equations. Once if you know the different subjects like fluid mechanics or heat transfer itself will answer almost 80% of the problems in solar energy system. Okay, so this will take later. Until that, I will take one more slide, which is the self-study topic. That is solar air heater, testing. All of you can see this slide.
Yes, sir.
Okay. So this is the self-study topic kept in this syllabus, which is in the new scheme. Earlier, this part was not mentioned in the syllabus. So as per my knowledge, this type of question, testing of the solar air heater, can be asked for 6 to 8 marks in the IA test or up to 10 marks in the exams. Also, the flat plate collector also can be tested, but as it is not mentioned in the syllabus or numericals are not mentioned for this part, so I have neglected that liquid flat plate collector testing. That is also in the similar fashion it is done. As it is mentioned in the self-study, even though it is in self-study, I have taken this to discuss so that one can understand how these all solar devices can be tested. Okay, so coming to this upper side, we need for a solar air heater, the artificial air heater can be used. We need a blower. We need pressure drop measuring devices. Then we need airflow measuring devices here, airflow or the fluid flow you can say, because if it is a liquid or chemical or water, I can say it as fluid flow measuring apparatus. Then we also need fluid reconditioning apparatus, or here it is an air conditioning apparatus or reconditioning apparatus. Then for measuring the temperature differences, because temperature difference itself tells us what is the useful heat gain or the heat transfer to the fluid, or what is the efficiency of the given system. So for that, at the inlet side and at the outlet side, you can see many thermocouples are connected here. 3 dots you can see at the inlet side and at the outlet side. Some thermocouples or the thermometers can be connected to find the inlet and outlet average temperatures. Then at the exit side of this solar air heater, the top of the side, orange color, if you see, the orange color shading is nothing but the solar air heater. Once the air is heated, it will come outside and it will start flowing. So that what will happen at the top side of the solar air heater, or once it is entering this duct, assuming the complete cross section is filled with air, in such case, top surface of the air will be having low temperature as it is near with the glass plate or the top plate. And the bottom plate, if you see, or the absorber plate, if you see at the bottom side, in such case, I can assume maximum temperature of the air will be at the bottom side. Okay, so to make that change in temperature from top to bottom side of the duct, so to overcome that difficulty, what we have done here is some vanes, small blade type, or the mixing of the flow to achieve. These vanes are used. Okay, so once this mixing of the fluid starts here at the entry and outlet of the vanes, what will happen at some section after some distance? I can assume that entire duct from top to bottom it is having same outlet temperature. So in that point, I will connect some thermocouples for finding the outlet fluid temperature. So this setup is almost similar to this liquid flat bed clay itself. Okay, only the results will be taken or the charts will be taken depending upon different mass flow rates for the aerator. So now coming to the working of this setup is, as you know, initially to heat the air there will not be any flow. So for that initial flow, one can go for the blower so that we can maintain a uniform mass flow rate of the air at the inlet as well as outlet. Or else, initially and while stopping the solar air heater working, I can use this blower so that if I stop the blower in the closed loop, so you can see here it is entirely closed loop. Nowhere the solar air duct it is not kept open to the atmosphere. Even though it is at outlet or inlet, it is not kept open. So in such conditions, this blower will help us to maintain the constant mass flow rate of the air at any condition or any temperatures. Also, this blower will help us to stop and run the system. Okay, it is acting like a pump. So blower will pump the air at the inlet side of the solar aerator, by which we are going to find out inlet temperature of the fluid. And as the solar aerator is having some slope, and also the surface, inside surface of this duct, if you see, it is having some friction, or it may be having smooth surface, whatever it is. From inlet to outlet, some energy will be lost in the form of pressure drop. So to measure that, what is the loss of energy or loss of pressure is taking place between these two inlet and outlet points, I can go for one of the U-tube manometer. Maybe water field is enough for solar air heating. For solar water heating, you can take mercury manometer to find the pressure drop. That is a change. So once the air or the fluid comes outside, now what we are doing, we are assuming that from top to bottom, temperature variation will be there. So to overcome that temperature variation after mixing with the vanes, what I am doing is, I am going to connect some thermocouples to find the outlet temperature, fluid outlet temperature, that is TFO at the outlet. Then once this is taken, this data will help us to find out the efficiency of the given air heater. So how to find that efficiency, we'll see later. Then again, as it is a closed loop, we are not taking any outside air. So what you have to do now, this hot air should be cooled. So to cooling air and again conditioning of that air, we need a air reconditioning or the fluid reconditioning apparatus. So once the required temperature or the ambient temperature of the air is achieved, then again it is taken to the blower by a air flowing measurement, because we need how much mass flow rate of the blower is taking place. So either you can connect this mass flow rate of air measuring device at the inlet side or at the outlet, wherever, because the mass flow rate will be maintained same. Okay, so this mass flow rate is also important for finding what is the useful heat gain by the air. In that case, we need mCp delta T, like a mass flow rate of the air, Cp of the air, then delta T. Okay, so this is about the setup and working. And coming to the data analysis. So before reading this question, I request all of you to go through this chart first. In such chart, you can see many different lines are drawn. So on the x-axis, temperature difference versus solar incident radiation curve is taken, or the data is taken. One more side, on the y-axis, if you see, the efficiency of the solar aerator or the solar collectors is taken. on the y-axis. So this type of arrangement and analysis is also done by Garg. So from the book you can refer Garg. He has also given the process how to be calculated these all parameters. So if you talk about the curves, in the liquid flat plate collector, if you focus, mass flow rate changing is very different for the liquid flat plate collectors, because as it is having pipes and the diameter of the pipes is fixed, and the quantity of water flowing, the velocity or the speed can be varied, but the mass flow rate, if you see, the variation will be very different. And also in that analysis, as the heat transfer coefficient of water and absorber plate remaining constant, no need of changing the mass flow rate in the liquid flat plate collectors. By using only one or two mass flow rates, one can observe many scatters of the proper efficiency at given different temperature differences can be observed. But in the air heaters, if you see in this curve, as the air heating is done, air is not completely in contact with the duct always. We can assume that air is always in the contact with the duct perimeter inside, but it is not sure. It depends on the different conditions. Because if the blower is blowing very low air quantity, or the mass flow rate is very less, then the density of the air also depends, and also depending on the temperature, the contact of the air with the duct will be depending. Okay, that is one difficulty. One more is the heating of the air will not be constant always, as in liquid flat plate collectors. So here what happens, as the air movement takes place between the duct at top side and bottom side, the heating will be different, due to which the heat transfer coefficient of the air also changes with different length, different temperatures, different mass flow rates. So that in this solar air heaters, what we have to do is, we have to take n number of mass flow rates, then we can plot the curves. So this curve will show us, depending upon the temperature differences and solar incident radiation, that is IT, how this efficiency will change. So just an example, I have not solved this problem. Just an example, I have taken this problem. You can see this example here. What they have given, the efficiency curve shown in the figure 1. Efficiency curves are these black colored inclined lines are the efficiency curves, and efficiency is shown on the y-axis, 0 to 70 degree. So between that, efficiencies are varying, and these values are obtained for a solar air heater of length L1 1.2 meters. So this L1 you can assume length of the solar air collector. L2 you can assume width. I hope you are understanding. L2 you can assume it as width of the solar air heater, 0.9 meters. So once you multiply this, I can get the cross section area of the collector or the plate. The connection is continuous, no?
Yes, sir.
Okay. Yes. So here efficiency curves are plotted. So for which this area was given here, L1 and W, or L and W you can say, length and width you can say, or L1, L2 you can say, for finding the area. So on which it is tested over a range of flow rates. See here, for air heaters, we can change the mass flow rate very easily. Okay, but here the efficiency cannot be changed apart from only changing the mass flow rate in the liquid flat plate collectors. So in the liquid flat plate collectors, other than mass flow rate, what they have done is they have changed the different temperatures and different solar incident radiations. By that, they have found out the efficiency of the flat plate collector, which is not in syllabus. I can understand, but for the solar air heater, what they have done, changing the temperature they have not done, because changing temperature means again many parameters will change for the air collectors, because heat transfer coefficient is a key factor here. Heat transfer coefficient for gases and air, which will be continuously varying. Okay, or the temperature variations with the duct and gases, it will be difficult compared to the liquids. So that's why what they have done, they have kept many parameters like solar incident radiation for a given day constant, and ambient temperature will be constant. Average temperature TF Average temperature means inlet and outlet temperature of the fluid. That also they try to maintain constant as they have given here. Outlet temperature, inlet temperature, ambient temperature, solar rate. All these things are kept constant. What they have changed the mass flow rate, and also area is also kept constant. Again, depending upon area, also efficiency may change. Okay, so one of the experiment done here is to check the efficiency is change the mass flow rate and keep all other parameters constant and find the efficiency of the collector. So question is, find the efficiency which would be obtained at the corresponding mass flow rate if the air heater is used under the following conditions. What are the following conditions? Inlet air temperature is 54 degrees centigrade. So maybe the country is having very high temperatures or hot conditions, because inlet air temperature itself is 54 degrees centigrade. And also in cold situation, if you see, after reconditioning, say for example hot air is coming out, reconditioning is not done properly. In such cases it may be hot air, depends. So that inlet temperature is 54 degrees centigrade. Air outlet temperature is 74 degrees centigrade. So after heating, the temperature is high, so 74 degrees centigrade. Ambient temperature is normal temperature, 26 or 27 degrees centigrade is given. Then solar flux or the incident radiation, total incident radiation, IT, which is taken in the ratio here, 950 watt per meter square, or as the unit in the graph is given kilowatt, you can write it as 0.95 kilowatt per meter square. Okay, so this is the values given in the problem. Then for what mass flow rate we need to find out? For 25 to 200 kg per hour. So for easy calculation, what they have done, they have taken each change of mass flow rate for 25 or 50. So like that they have plotted some values here, 25, 50, 100, 150, 200 like this. So for each 50 kg per hour, they have plotted the values. Now question comes, how they found out these values? So one thing is, first we need to find out this TF. So TF bar means the average temperature. So average temperature of fluid, if you find out, okay, in that case you have to take the average temperature of inlet and outlet temperature. Then ambient temperature minus TA is ambient temperature 26 degrees centigrade. So by that one can find out this TF value minus TA divided by IT. So IT, as I told you, kilowatt, you write it in 0.950 watt per meter square. So for that value, you will get one constant value. I'm not talking about complete curve. I'm talking about one value. For a given value in the problem, how to find out efficiency. So for given one value of this ratios, say for example, you may find out for 30 or 50 in between that, or 40 if you say, I may get at 40 what may be the efficiency if it is 25 kg per hour. So efficiency will be how much? It is around 25 or 24 efficiency. Then for efficiency, as you know, it is a ratio of useful heat gain by the fluid in the numerator to the total heat supplied. Heat supplied means the solar flux supplied. Okay, that you can take. So by that one can find out the solar incidence from that, how much heat is gained by the fluid. So by taking that useful heat gain to the total heat supplied, one can find out this efficiency percentage. Okay, so similarly, say for example for 50 kg per hour, so only mass flow rate is changing, not the value of this ratio of temperature and solar constant for a given problem. But if you go on changing these values on x-axis, depending upon the temperature and solar incident radiation, so as the value of this ratio of the temperature and solar radiation ratio changes or increases, what will happen? The efficiency goes on reducing. Why? Because as the average temperature of the fluid increases, okay, or the inlet temperature itself increases, efficiency will come down. The meaning is, I want to tell you, for any solar air heater or the heat exchanger also you can take in a heat transfer subject to understand more is, the inlet temperature of the fluid should be maintained very less. Then only any fluid can absorb more heat. If the inlet and outlet temperature maintained equal, there is no heat transfer. Efficiency will be zero. in the similar fashion, even though if you go for inlet temperature more than outlet temperature, then what happens? The air may lose the heat, and the entire heat exchanger or the liquid calculator of the air heater itself gets heated up from the fluid. That also, in that case also efficiency will be less only, not more, or it may not be positive also. That's why what I'm going to say is, whenever you maintain this average temperature or the inlet temperature of the fluid as much as less possible or low as possible, then one can achieve maximum efficiency. See here, at 0 to 10, if you see the value, efficiency is around 40 to 60 for different mass flow rates. Is that clear? If the temperature at the inlet side of the average temperatures are very high, say for example, for this given ratios, it is 80. In that condition, if you see the efficiency, 10 to 20 is not preferred also. That is what we want to discuss about this solar air heater testing by changing this mass flow rate. Okay. So similarly, in that fashion, we are finding this efficiency values, and also question comes how to find this useful heat gain. So useful heat gain, as I told, MCP delta T, mass flow rate of the water or air, CP of the air you can take from the data. Okay, and delta T. Delta T is inlet and outlet. Inlet and outlet temperature is fixed for all the problems. But what is going to change here? Mass flow rate is going to change. So that will be the useful heat gain by air. Total heat supplied for the collector is given in the data itself. Okay. So as per this problem, only one value you are finding, like for 50 how much, for 40 how much is the efficiency. And for different mass flow rate, we are getting some different points here. So once you plot for taking different temperatures, then the different mass flow rates all together, I can plot the curves like this, which are in almost straight lines as is shown in the sketch here, but it will be a little bit scattered. Some points will be outside. We are drawing best fit curve. So these all curves will be best fit curves, which are showing us maintaining the inlet temperature as low as possible and maintaining the outside temperature as high as possible will give us more efficiency, provided the mass flow rates also should be more. Okay, if in the heat exchanger mass flow rate of the air or the liquid is very less, suddenly the efficiency of that collector will be less because of the less contact between the inner surface of the tubes. So that is the meaning. So this is about solar air heater testing. So I think next Thursday, your assignment is planned. So in the assignment, I will be asking unit 2 questions. Okay, if possible, this air heater will be included. Okay, second module as well as this solar air heaters.
Okay, sir.
Okay, coming to the last part, numerical. I'll take this numerical and we'll finish off this part.
Okay, sir.
Yes. So all of you note down carefully. A flat plate solar collector, 1 meter wide and 3 meters long. So length of the plate is 3 meters. Width of the plate is 1 meter. A flat plate is taken. Whether it is air or liquid, we don't know. So this is used for air heating purpose. Now it is clear by this word. It is a air heating purpose they are using. So one should note down this L1, L2, or you can note down it as W and L. 1 meter, 3 meter. Air at 40 degrees centigrade and 1.01325 bar pressure. That is the normal pressure. So air at 40 degrees centigrade and 1 bar pressure is following through a collector with a velocity of 4 meter per second. Velocity of the air is also given. The absorber plate and glass cover are located 5 centimeter apart. Now by this one can understand between glass cover and absorber plate, air is flowing where the air is heated in the duct. And the distance between will give us the height of the duct. Height of the duct is 5 centimeters. Length of the duct is 3 meters. Width of the duct is 1 meters. Are you getting the point? For cross section, I can use width and height. For characteristic length, I can go by 3 meters long, like that. The solar heat flux falling on the collector, which is the incident radiation or the total incident radiation from the solar energy, is 630 watt per meter square, or I can say 0.630 kilowatt per meter square. Find out temperature of air coming out of a solar collector. See, out of this complete question, the required thing is only outlet temperature of the air you need to find out. That's all. But what is all procedure you have to follow? You see. In the question itself, they have mentioned, assume transmissivity tau of the glass cover 0.85. Absorptivity or the absorber plate absorptivity is glass cover absorptivity or the alpha value is 0.9. Okay, this much value is given. So tau alpha is given means we have to go by that glass cover system for the liquid flat plate collector. What we studied in transmissivity and absorptivity product, which will give us the maximum solar radiation absorbed by the plate. So that also we have to follow. Use the following air property. What is given? Mu is given 2.07 into 10 raised to minus 5 kg per meter second. That's coefficient of viscosity. Cp is given 1 for air. Okay, for air it is given 1.005 kilojoules per kg per degree centigrade. Then Prandtl number PR is given 0.698. K is given 0.03 watt per meter Kelvin. Use the following correlation. This is also given. See, properties of air is given. Assume transmissivity and absorptivity is also given. Dimensions of the flat plate collector and the inlet and velocity and solar incident radiation. See how many parameters for finding only outlet temperature of the air. It is not MCP delta T. By delta T one can find out outlet temperature. It's not so. It's some different thing. So correlation for Nusselt number is also given in the problem. What correlation you have to use? Earlier by theory we saw this Nusselt number. But as for this problem they are mentioning this. Using Prandtl number also you will find out Nusselt number. That is 1.86 Reynolds number into Prandtl number raised to 0.50. I think in heat transfer you have come across this type of correlations for laminar flow. Also, if it is turbulent, Nusselt number can be used as 0.0196 Re raised to 0.8 PR raised to 0.50. This is Prandtl number. Okay, so you can note down this given data. Take 1 minute time. Then later we will go to the solution step by step. Shall we proceed? Karan?
Hi, sir.
Okay. Yeah, next now and come to the analysis of this problem. So as I told you, dimensions of the duct is given and air is flowing between absorber plate and glass cover. Because in some problems also they may tell between absorber plates, because top plate may be heated by transferring the light from glass, and air duct will be maintained between the two absorber plates or two metal plates. That may be the different condition. But here the condition is very simple. It is passing between glass and absorber plate. That's why they have mentioned transmissivity and absorptivity. Okay. Yes. Now, first thing is to find out the total solar radiation falling on the absorber plate after light is transmitted through the glass cover. So one thing is that we can do, or else directly they have started from the whether the flow is laminar or turbulent. Anyway, you can solve because here you can see. Yes, here S into tau alpha into area of the surface. This also you can find out how much is the heat falling on the plate or heat absorbed by the plate. That also you can find out first. You can equate with the heat carried away by the air and you can find out one of the temperature. Or else first you can find out this turbulency of the given system. So to find that whether the flow is laminar or turbulent, we all know that we are going by Reynolds number, rho Vd by mu. So here d is the length of the given system or the height. Just a minute. This d for given d value, they have taken 5 by 100, I think 5 centimeter height. They have considered this cross section height. How much is the cross section height? Which is between glass and plate in which the flow is taking place. And velocity is given in the problem 4. Density is not mentioned in the problem. In one of the liquid flat plate collector, I remember density of water was mentioned in the problem. So directly we have substituted. Mu is given in the problem. Directly you can substitute, that is 2.07 into 10 raised to minus 5 kg per meter second. That is given. Now how to find out density? So density for the gases can be found out by taking this relation. What is that relation? Rho into RT equal to P. Or I can say density for given air can be found out by using PA by RT. So P is given 1.01325 bar is given. So convert that bar into pressure in SI units. That is 10 raised to 5. Divided by real gas constant 287 and temperature in Kelvin 40 plus 273. To take, because it is a gaseous system, they have taken this P by RT to find the density of air. The density of air is coming around 1.13 kg per meter cube. So using this density in this Reynolds number, they have found out the Reynolds number. It is coming around 10,918. So by number itself, one can judge it is a turbulent flow. So please calculate or follow the process. If any mistakes or anywhere doubts are there, you can ask. So once this Reynolds number is decided, now I can decide what type of Nusselt number can be used so that one can find out the heat transfer coefficient between air and the surface, or heat transfer coefficient by convection. So now I'll go back to the question. So as the flow is turbulent, I'll go by this Nusselt number 0.0196, RE raised to 0.8, PR raised to 0.33. See here. So same equation we have used in place of HL by K. HL by K is theoretical. If you know the H value, characteristic length and K value, I can go by this equation. But here we don't know H, how much is H value. So to find that, we are going by correlations. And in the correlations, they have mentioned Reynolds number as well as Prandtl number. So I can use that Reynolds number 10,918 raised to 0.8. Prandtl's number given in the problem 0.698. Prandtl's number here 0.698, which is a dimensionless numbers. So using these correlations, now Nusselt number is 29.6. Now using this and theoretical Nusselt number equation HL by K, I will find out what is h. So here, please remember the characteristic length we have taken the height itself. Okay, the height itself we have taken characteristic length. K is given in the problem 0.03. Nusselt number is 29.6. And now, what is the H value heat transfer coefficient by convection? It is coming around 17.75 watt per meter square degree centigrade. If it is coming any other value also, please suggest. We'll make changes in the problem. So this is the procedure just to find out H value. Have you understood why the Prandtl number, Nusselt number, Reynolds number, or any parameters with respect to flow or the velocity is given in the problem? Then one should find out useful heat gain or heat transfer coefficients by radiation, convection, or conduction, depending upon the different heat transfer phenomena. Then one of the equation we can find out the temperatures. So this H value may be used in this heat balance. What is that heat balance? In the performance we have seen, heat balance is heat absorbed by the plate and heat gained by the air. That is the balance. So theoretically we assume always whatever the heat transferred by the heat exchanger or the air heater, that heat equally it will be absorbed by the fluid also. But experimentally it is not possible. So assuming that balance, if you see here, to find the exit temperature, we know that heat gained by the air will be equal to heat absorbed by the plate. So in that case, what they have done? They have taken heat absorbed by the plate as total solar radiation incident for a given surface area A with transmittivity and absorptivity losses, because glass will absorb some heat that is not directly transmitted to the air absorber plate, because the system is not kept completely open to the atmosphere. The glass cover is there. That glass cover is having some heat energy, or it is going to absorb some heat energy. Okay, so that is given by tau into alpha. That is considered there. S into tau alpha surface area. So surface area, how you find out? Surface area of the conductor is length into width. So that length into width is given 1 meter by 3 meters. 1 meter by 3 meters is the surface area. This equal to heat gained by any fluid is given by mCp delta T. Inlet and outlet temperature difference. M is the mass flow rate of air. Cp is value of the air is given in the problem. Okay. And in this, to find the mass flow rate, as I told, by continuity equation of the real fluid equations, area into velocity, AV, into rho, if you multiply, one can find out mass flow rate of fluid. So again, you can take their area of cross section. So what is the area of cross section? Area of the cross section at the top surface. See, for the airflow, cross section is different. Height is 5 centimeter, length is 3 meters. Focus here. Airflow duct is 1 meter by 3 meters length. Okay. Sorry. For airflow, height of the duct is 5 centimeter, length is 3 meters. For the collector surface area is the top or absorber plate, if you see, that is having this distance 1 meter wide, 3 meters length plate is there. Glass plate or absorber plate, both are taken same. Height will not come into picture here because we don't want duct, we want only surface. So on that surface, how much air will be passing? Okay, so area of the cross section for the air will be different. Surface area of the plate will be different. So for cross section area of the duct, we have taken 5 centimeter height, we have converted into meters. Then it's 3 meters long. 3 meters long, and velocity is 4 meters. So cross section, what we'll do? you can take only 5. Okay, 5 is the duct passage. Width is 1 meter. That's why they have taken 5 centimeter into 1 meter. So after converting that 5 into 1 into centimeters, they have taken like this. 4 is the velocity of air. Density of air is also found out earlier, 1.13. So from this one can find out the mass flow rate of air, 0.226 kg per second. So this value you can substitute now. So all the values you can substitute like mass flow rate of air, how much it is getting, MA value 0.226, or you can take the top equation and you can substitute all the values. Heat absorbed by the plate. Solar incident radiation is 630 watt per meter square into tau is 0.85, alpha is 0.9 into surface area 1 meter by 3 meters, length into width of the plate into or equal to mass flow rate of air is 0.226 kg per second into here what is that Cp value of air 1005 into T naught minus T inlet. Inlet temperature is known to us 40 degrees centigrade. What is that given inlet temperature of the water? Here air at 40 degrees centigrade is given in the problem. Also this Cp value of the air 1.005 is given. You can take it in 1005 joules per kg degree centigrade. So that value is taken. Now T naught will be outlet temperature of air. It is 46.4 degrees centigrade. Okay. So this completes the problem. So take another half minute to understand, and we'll stop the class here. Next Monday class will take the solar concentrating collectors. Okay, so this completes solar air heaters with self-study. So this type of problems, balancing the heat, you can see in the heat exchanger chapter in heat transfer subject. Similar type of equations, but here tau alpha is different for the solar collectors. And S value is also heat supplied. So heat supplied will be different in the heat transfer subject. Heat supplied in the solar subject is solar incident radiation itself. Only that is a change. So if you compare heat transfer subject with solar devices, the concepts will be clear. Shall I stop the class?
Okay, sir.
Okay.